So, in our course selected topics in decision modeling, today we shall discuss the exhaustive enumeration and branch and bound techniques as applied to integer linear programming problems. Is all right. So, what we do here in the exhaustive enumeration and branch and bound techniques, there are two different techniques, and both the techniques are essentially can be called as enumeration techniques, right. So, both are enumeration techniques. And what happens in enumeration techniques, systematically we generate and evaluate all possible solutions and choose that those feasible solutions and with the optimal value. So, obviously out of many feasible solutions, one that will give us the best solution will be our optimal solution. So, that is how we do exhaustive enumeration. So, we look at all possible solutions. Whereas, in branch and bound we divide the large problems into smaller sub problems. The sub problems should be divided in a particular way, so that they are mutually exclusive and collectively exhaustive. I will explain that, and then there should be two mechanisms. One mechanism to branch out those subsystems, that means break them into smaller subsystems, and a mechanism to generate a bound. The bound means best possible value at that sub problem level, and then the examining the bounds we try to find out the optimal solution. So, it is very interesting method, the branch and bound. So, we will explain that also, but before that let us look at in detail what is this exhaustive enumeration method, right. So, let us take a simple problem. Systematically, how do we generate a linear programming problem? What is that problem? Maximize z equal to 3x1 plus 2x2 subject to x1 plus x3 less than equal to 3 and x1 plus x2 greater than equal to 0, and x1 and x2 are binary. Is it all right? So, how do we solve this particular problem? What are the all possible solutions? Can you think and tell? Very simple problem, x1 and x2 are binary. So, what are all possible solutions? Just think over that, since it is all binary. So, x1 could be 0 or 1, x2 also could be 0 or 1, right. So, that means x1 equal to 0 and x2 equal to 0, x1 equal to 0 and x2 equal to 1, x1 equal to 1 and x2 equal to 0, x1 equal to 1 and x2 equal to 1. They could be our all possible solutions. So, very easy really. So, because it is a very simple problem. So, that is what we put it in this manner. So, you see at P0 level, x1 is, that is the initial level, we put x1 equal to 0 or 1, x2 equal to 0 or 1. Then we branch, x1 could be 0 and x1 could be 1. That will give us a problem which is maybe called as P1. At this x1 equal to 1 and x2 is 0 or 1, here x1 equal to 0 and x2 could be 0 or 1. Then P1 is again divided, x2 equal to 0 and x2 equal to 1, then we get P3 and P4, P5 and P6. So, what is P0? P0 is the original problem, very clear. What is P1? P1 is the problem which is this with x1 equal to 1. P3 is a problem which is x1 equal to 1 and x2 equal to 1. Similarly, P4, P5, P6. Now, look here, the original problem P0 we would like to solve. By enumeration we found that basically the solution of P0 is the best possible solution of P3, P4, P5, P6. So, where we had only one problem, we now have 4 different problems with 4 different solutions. The best one amongst them going to be our optimal solution, right. So, this is what exactly we do in exhaustive enumeration. We have enumerated all possible n nodes are found, every n node is a problem, right. That is the original problem with some additional conditions, right. But collectively all of these small problems, not really small conditional problems, they are all collectively define the total problem. That is what is exhaustive enumeration does, right. So, if that is so, then we can now find out the solutions for these 4 problems. Very easy. If x 1 equal to 1 and x 2 equal to 1, z star will be 5. If this is 1 and 0, it will be 3, 0 and 1 it will be 2, 0 and 0 it will be 0. So, this is the objective function values written. As I said, what is the objective function value for P 0? It is the best possible value out of these 4, because these 4 problems collectively define all the possible cases of P 0. Actually, we are trying to solve P 0, not P 3, P 4, P 5, P 6. The best solution for P 3 is 5, P 4 is 3, P 5 is 2 and P 6 is 0. Alright. Out of that, 5 is the best. Since 5 is the best, now it is clear the best solution for P 0 is x 1 equal to 1, x 2 equal to 1 and z star equal to 5. See, we are not interested in solving P 3, we are interested in solving P 0, right. P 0 is, P 3 is one of the cases of all possible enumerations and the solution of P 3 comes out to be best. So, that is the optimal solution for our original problem, that is P 0. I hope you understood. That is how by exhaustive enumeration we can solve such problems. Anyway, it is fairly easy, very simple problem we took. So, there is nothing much to worry. Let us see a slightly other issues. The problem is that if we are really doing binary bifurcation, so if number of binary variables are 2, number of enumerations are 4. If we had instead of 2 variables 3 variables, number of enumerations would be 8. If we had 10 variables, enumerations will be 1024. And when you go to 50, if we had 50 variables, then the binary enumerations would have been 1.126 into 10 to the power 15. You can imagine it is a high number, right. So, if you do exhaustive enumeration, it might lead to very high computational complexity. Is it okay? You may have to really evaluate a very large number of problems. You can say I have big computers, what is the difficulty? But how big is the big? There could be problems in reality which may have 1000 binary variables, and then the problem size would be so large that you may require years, 10 years, 20, 30 years to solve a large problem. We do not have that much time. We need to solve the problem in a reasonable time. So, exhaustive enumeration or a kind of brute search is a method, but not always applicable, because it makes the problem computationally so large, so complex that we simply cannot think about it. We must have efficient method, right. And one such efficient method is branch and bound. But before going to branch and bound, let us see one more example. So, let us say a 0-1 knapsack problem by exhaustive search. Let us say we have 4 items, item 1, item 2, item 3 and item 4 with a weight and a value, and this weight and value, we need to maximize the value within a certain knapsack capacity. How do we go about? Obviously, the formulation is maximize z equal to the total value 16 x 1, 22 x 2, 12 x 3 and 8 x 4 subject to the weight restriction, that is 5 x 1, 7 x 2, 4 x 3 plus 3 x 4 less than equal to 14. And additionally, it is a 0 1 knapsack, that means each item can be either there or not there, as simple as that, right. So, generate all possible subsets of n items, that is how we shall go about that, all possible combinations, right, and compute total weight of each subset and see whether it is feasible or not feasible. Then find the subset of the largest value 2 to the power n possible subsets that will be generated. So, that is how we go ahead with this 0 1 knapsack problems, right. So, let us see what are some possible generations. So, look here, these are the generations. First of all, you can have null set, then you can take only 1, we can take 2, we can take only 3 or 4, then we can take combinations like 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4 and then 3 and 4, right, 6 combinations. And then also we can have 1 2 3, 1 2 4, 1 3 4 and 2 3 4 and finally all 4 of them 1 2 3 4. So, that is 1 2 3 4 5 then 6 11 then 4 15 and 1 16, is it not. So, that is what 2 to the power n, that is 16 possible combination that we could have under this situation, that is 2 to the power 4. So, 16 possible combinations are there. Now, what we can do for each combination, we can find out what is the weight and what is the value, and based on the weight whether it is becoming the feasible or infeasible, because if the weight is more than 14 then it will become infeasible. Okay, fine. So, then we see where we reach. So, we see that as we evaluate, then we find for null set both are 0, for 1 2 3 4 it is only the weight and value as given. If we take 1 and 2 then it will become 5 plus 7 12 and value is 38. Like this, for each of these we can write down the weight and the value. We see that total weight crosses in some situations. For example, here and here the total weight is crossed. So, these since they are crossed, they are all infeasible, right, these solutions are not practical. So, out of these remaining solutions, which one shows the maximum possible value? Just look at carefully, this 38 is good, but this 42 is the best. So, the best solution comes in the combination where we take the items 2, 3 and 4 with a total weight of 14, that is within the knapsack, and with a value of 42, is all right. So, that is our best possible solution. So, by exhaustive search we can find out the problem of the knapsack problem, but for only 4 items we had 2 to the power 4 different searches. Think of 10, then it will be 2 to the power 10, right, 20 items 2 to the power 20. So, there are lots and lots of such combinations which we have to search, and it could be complex, very complex and computationally challenging. So, may not be possible to solve, right. So, let us see then another way of solving this problem, which may be called as branch and bound technique. So, how this branch and bound technique is and how we go about it. Again I repeat, what is really a branch and bound method is that it's basically a divide and conquer method. So, we break a large problem into a smaller sub problems, and you need, as I said, two mechanism, a mechanism to generate branches, a mechanism to generate a bound, so that many branches can be terminated. So, how do we go about it? So, that is our branch and bound technique. So, as you see, this, look at this example, what we have done, supposing this is our total problem, the total problem is, this is our total problem, the total problem is divided into two sub problems, SS1 and SS2, and SS1 and SS2 must be mutually exclusive, but collectively exhaustive, right, mutually exclusive, but collectively exhaustive. See, it is not necessary that we have to divide in two only. Let us take a simple situation. Supposing I have 3 people A, B, C, and these 3 people are doing 3 jobs J1, J2 and J3. Now, these are the times which are taken by A, B, C. All right. So, who should do which job? So, this is the time required to do job, right. A does the job 1 in 10 minutes or 10 hours, B does in 9 hours, C does in 8 hours, sorry, A does the job 1 in 10 hours, job 2 in 9 hours, job 3 in 8 hours, B does in 9, 8 and 7 and C does in 12, 10 and 8 hours. Now, who should do which job so that we can do all the 3 jobs in the minimum possible time? So, first of all, we have to do, if we have to solve this problem by branch and bound technique, first of all we should be able to quickly find a bound. How do I find bound? See, this is a minimization problem, because we need to find out who should do what minimum possible total time. This is what we want. Who should do which job in minimum possible total time. So, it is a minimization problem, and we really find out then the lower bounds, LB. What is LB? Lower bounds. So, how do I find out the lower bounds? So, can you quickly find out a lower bound from this matrix? Supposing we find out row wise, then 8 hours that is lowest, 7 hours that is lowest and 8 hours that is lowest. So, 8, 7, 8, 23 hours is the lower bound, So, you see, if only job 3 would have been done by A and B and C, the job could have been done in 23 hours. But then we need to do all the jobs. So, just doing J3 is not enough. So, this 23 is a lower bound, no problem at all, but this 23 is infeasible, right. So, we have found a lower bound 23, which is an infeasible solution. Now, how do I make branches? So, supposing we make 3 branches. What are the branches? A does J1, A does J2 and A does J3. You see, A has to do either J1 or J2 or J3. There are 3 people, 3 jobs. A has to do either one. Supposing A does J1, then this line is gone. That means, A has to do J1. So, out of the remaining, this is this matrix, which is the lower bound? Again we have 7 and 8. So, 15 and this 10. So, 25. So, this 25 is the lower bound, again it is infeasible. Why? Because B and C both are doing job 3. So, it is an infeasible solution, is all right. So, you see what we have done, the original problem we have branched into 3 problems, and for each problem we are finding the bounds, all right. If A does J2, then these 2 lines will be gone. So, let us write once again 10, 9, 8, 9, 8, 7, 12, 10, 8. So, J1, J2, J3, A, B, C. So, A does J2. So, this is gone. So, A will be 9. Now, which is the lowest? Again these are lowest, 7 and 8. So, what is the bound? Bound is 24, but it is infeasible again. But if A does J3, so again let us see 10, 9, 8, 9, 8, 7, 12, 10, 8, A does J3. So, then you see again the lowest is 18 here and this 8 here. So, this is 26 infeasible. So, we are getting all infeasible solution, but then you see A to J2 looks promising because this is 24 infeasible. Then if we go further, then again now B has to do either J1 or J2. So, look here, then we find B to J1 and B to J2. So, we dig it further, right. So, if now B does J1, look, so this is also gone. So, B does J1, then C has got only one choice, C has to do J3 only. So, you see that time is 26 feasible, it is a feasible solution, because A to this A to J2, B to J1 and C to J3 is a feasible solution. But then if B does J3, then C has to do J1, then that time is 27, again feasible. So, you see now if we look here, something interesting has come up, that B to J1 26 feasible, B to J2 27 feasible, A to J3 26 infeasible and A to J1 25 infeasible, right. Now, which is the lowest? Lowest is 25. So, we have to explore A to J1 further. Supposing arbitrarily I am saying, now if we explore this further, we might find a value which is higher than 26. Supposing arbitrarily, I am not doing it, supposing I find 30 here and 31 here, suppose. Then you see out of 30, 31, 26, 27 and 26 infeasible, this is the 26 feasible is the lowest also and feasible also. That means, the solution obtained in this branch is the lowest amongst all the different branch values and at the same time feasible. So, when that happens, we find an optimal solution, right. So, this is how it goes, that we divide the problem into different subsystems and those subsystems should be mutually exclusive and collectively exhaustive, is it all right, and in each we find a bound. It could be lower bound for minimization and upper bound for maximization. Once we find the bounds, then keep on branching till you get to a point where a particular branch is fathomed, that means we cannot go further into that branch anymore. So, when that happens, we have found the best possible solution by observing all the n nodes and finding the best possible bound values. As we see more and more examples, our concept will be clear. So, let us look at a little more theory and let us see some of the things. So, these are 3 basic steps. So, first one branching, bounding and fathoming. right. So, what we did, each problem we branched and then we found bound for each branch, and accordingly each branch we should know where to stop, that is called fathoming. Branching, choose one of the variable whose value will be fixed to create n new sub problems. So, you see the problem that we took, we fixed that a to j 1 or a to j 2 or a to j 3. So, when you fix, then you created certain sub problems which are obviously mutually exclusive, and collectively if you add all of them, they should make the total problem. So, that is how we do the branching, that is the first step. Now, after branching, next step is bounding. Now, I have shown you one type of finding bound values, but there could be other methods. So, a bound is an optimistic estimate of the solution of a problem. Solving the LP relaxation of a sub problem will yield an optimistic estimate of solution. So, you see, if it is an integer problem and we can solve an LP, then LP can give a bound value. It is not necessary that all the time you have to solve an LP only, like the example I gave, you can find bound by certain other methods also. But then typically if we are solving a non-linear integer linear programming problem and we have a non-integer problem solution, then the LP solution can give us a lower bound for minimization and an upper bound for maximization, right. So, LP relaxation of an ILP is a valid bound, and bounds can also be found in other ways, like assignment solution provides a bound for the travelling salesman problem. Later on we shall see, if we are trying to find out travelling salesman problem solution, then we can solve an assignment problem and the solution we find can be used as a bound for the travelling salesman problem. Like these ILP that we solved in our previous lecture, right. So, this problem we have solved by simplex, and then we found the optimal solution was x 1 star equal to 10 by 3, x 2 star equal to 0, and z star was 2 x 1 plus x 2 equal to 20 by 3. The present optimal solution is non-integer, right. So, an upper bound for the ILP problem will be 20 by 3, right. So, the LP solution could actually be used as a bound, all right. So, that is how it is, and when it comes to fathoming, three situations may arise when we no longer need to resort to branching. What are those three solutions? A sub problem is fathomed if its LP relaxation's optimal solution is integral. That means, we find an optimal solution and we find it is an integral solution. Its bound is worse than the best solution found so far. So, you see, something becomes fathomed that we find a bound, but then there are some other bound at a different problem which is providing a better value. So, lower than the lower bounds, lowest of the lower bounds are elsewhere. So, we find a lower bound here which is higher than a lower bound elsewhere. So, that means this one is fathomed, and the LP relaxation has no feasible solution. By LP relaxation we found an infeasible solution, that means also we can stop there, right. So, by making use of the bounds, the branching and the fathoming, right, we can solve the branch and bound algorithm we can make use of, and in our next class we shall take proper examples of how to solve branch and bound, use branch and bound techniques to solve general purpose problem. Is it all right? And specifically further we shall spend more time in solving travelling salesman problem by branch and bound technique, right, in further classes, right. So, stop here. Thank you very much.